Okay, welcome to physics today. This is where we left off last week with Boyle's law. And our formula for Boyle's law is P1 times V1 equals P2 times V2. So we're going to do a couple problems here just to see if you guys remember how to do this. Okay, so this problem says at 27 degrees Celsius, it should say an amount of gas has a volume of 2 liters. What will it occupy if it is heated to 87 degrees Celsius? That was Charles' law. Here's the Boyle's law. I messed up on that. We are going to do that today, but not first. We're going to kind of warm up. So here's the first problem I want you to do with Boyle's law. If the pressure on 2 liters of gas at normal atmospheric pressure was increased to 1,520 millimeters of mercury, what would the final volume of the gas be?
Like the volume of the first number that was volume 1.
Sure. So everyone knows how to count. It's 1 and then 2 and then 3, 4, 5, right? So 1 comes first. So just remember that that's what that means. So look up in here. What's the first pressure? It says if the pressure on a 2-liter gas, that's not pressure. That's volume. But that's the first volume they're talking about, right? So we can just say this is going to be the first volume. And it's of a gas at normal atmospheric pressure. That's where this is the whole story problem, where you have to know that number. So normal atmospheric pressure is either 1 atmosphere. So 1 atmosphere, these are the numbers we talked about, 101.3 kilopascals. Those are both the same pressure, but they're measured differently. Or 760 millimeters of mercury. Okay, so if you look at this, it says at normal atmospheric pressure. Well, this atmospheric pressure here then is P1, and it happens to be normal atmospheric, which is 760 millimeters then. So that's the number for P1. That's the hard part right there. The other number, or the other name for pressure is torr, and it's the exact same number as millimeters of mercury. But we don't need to know that for yet. Okay, so that's P1. We found V1. Now, is this a pressure or volume? That's pressure, and it says it's increased too, so it means this is what's going to happen next. So 1 happened first, now 2 is happening, so this one would be pressure 2. The thing we're actually looking for here is V2. So then we just plug and chug, is what we say. So P1, we've already got it labeled, 760. I'm going to leave the labels off because I know that they're there. And then we have 2 for my liters of gas. P2 is 1520. And then I have V2. So do you know how to solve for V2 now, algebraically? Do you have a And so here you just divide both sides by 1520, right? 1520, and it happens to be, I think, that 760 times 2 is 1520.
So it just turns out to 1 liter.
Yeah, so this is canceled out. So V2 then equals 1 liter. And that's when you want to make sure you have the label on as every final answer, so I know you're doing it correctly. Okay, let's try another one. Okay, so this is still Boyle's law. And I think the hard part of this stuff is probably not the math, but probably the whole kind of story problem. Trying to figure out where to put your variables. Okay, so this is Boyle's law here. I'll let you do this one. Try it. Okay, so this one was easier because we were given the pressures instead of just having to know what normal atmospheric pressure is. So for this, we plugged in the numbers. Now we just have to divide by 1,000, both sides. And our final answer then is P2 is equal to
1,260.
16 milliliters. Okay. Oh, wait, no. If we're looking for pressures, it's is a millimeter, or millimeters. And what that is if I have a tube in a bathtub of mercury, and up here is only mercury vapor, according to the pressure that's pushing down on the fluid, that's how high this mercury level will go up in the tube. And it starts at, 0 millimeters, and then this has gone up 1,260 millimeters, which is pretty high. Okay, so.
Wait, would that be actually like high up?
Okay, now we're going to talk about one more gas law. Now, we've talked about all these gas laws, but it's all about the kinetic theory. And the people that kind of came up with these ideas, they were great thinkers, and so therefore they have these laws named after them. But it's, it's all talking about the same thing. So whenever you think about gas or gas laws, think about the kinetic theory of the movement of the particles. Think about temperature being the speed, or the average kinetic energy of the particles. Think about what happens when the particle hits something. It applies a force to it. And so all those things here, all the laws are described by the kinetic theory itself. So those things I talked about would be all laws. So let's say that we have a balloon, okay? Now, there's a fixed volume of gas in there. Okay, so, or I shouldn't say there's a fixed volume, there's a fixed amount of gas. So in other words, I'm not going to put more particles in or take less particles out. I've got a question for you. What pressure does, if this balloon here, let's say that we're at San Francisco, this is the ocean. Can you tell me if the balloon has no elasticity to it, so in other words, it doesn't like push on the gas itself, what pressure does the gas inside the balloon have? Okay, the answer then is 1 atmosphere of pressure. Because we have this whole atmosphere of gas pushing down on the balloon, but it doesn't just push down, it pushes in all directions, right? Because these particles are constantly colliding with each other. So they're going in all directions. So what I have here then is atmospheric pressure. And it's pushing on the balloon in all directions. And that's 1 atmospheric pressure pushing inwards. If the pressure inside the balloon did not equal that, what would happen to the balloon? Right, so if the pressure inside the balloon was smaller than 1 atmosphere, it wouldn't force as much as the outer. So the balloon would get smaller, do you agree? And if it was bigger on the inside of the balloon would get bigger until there was this equilibrium of pressure inside and outside of the balloon. Okay, so now that we understand that the pressure inside the balloon equals the pressure outside the balloon, regardless, the question was, well, geez, if I have a helium balloon and I go outside and it's cold out, it gets smaller, right? So let's just say that this is the helium balloon right here, okay? And we know that this helium balloon has a bunch of particles in it, and they're going fast, right? In all directions. And that is called temperature. Do you agree? The speed or the kinetic energy of the particles is temperature. Okay, so let's just say that we're inside. 20 degrees Celsius is approximately room temperature inside. Let's say we take this balloon, so here's the inside. Okay, we'll take this balloon outside and it's 0 degrees Celsius. What's going to happen to the gas inside the balloon? Is it going to get colder? The gas is going to get colder, and the best answer is the gas is going to slow down. So when this slows down, let's say when it's hot, it's going this fast, and it hits the edge of the balloon. When it slows down, it's going this fast. What's the difference between those two temperatures as far as when it hits the side of the balloon?
Faster one is hotter.
The faster one has more temperature, but when it hits, like, think of force. So this is the fast one, this is slow one. It's a harder hit. It's more force. Do you agree with that? And that force, keep in mind, pressure is force per area. So if I have less force, what's going to happen to the balloon? The balloon is going to get smaller, exactly, because it has less force from each particle hitting the side. And so it has to get smaller. Now here's the next question though. How is the pressure in here versus out here?
It's lower, so the pressure on the outside is down.
Okay.
In up.
Okay, that's what happens while it's getting smaller. But once it doesn't get any smaller, what is the pressure inside versus the outside? It's going to be the same because it will stop at some point. It won't be. Yeah, once it equals the pressure on the outside, then the volume change is done. So does that make sense? Now the temperature is the speed of the particles. If I have a slower speed, I have less force. And if I have less force in this case, I won't be able to keep my balloon expanded as much because there's not as much force. So I get a smaller balloon. So that then is what you want to write down here on your last bit of notes. It's called Charles' Law. So everything we talked about can be explained, everything that you just explained, or we just explained, is Charles' Law. So the classical definition is right here. If the pressure on a dry gas is kept constant, its volume will be in direct proportion to its Kelvin temperature. Okay, so that's a big important thing right here. We need to make sure that when we put our temperature numbers in, it's in Kelvin. Because that, like if I have 10 degrees Celsius and negative 10 degrees Celsius, I come up with the same number but a negative, right? But 10 degrees Celsius versus negative 10 Celsius is 263 Kelvin versus 283 Kelvin. Okay, so in order for us to do this math right, we need to make sure that we're using Kelvin temperature. Okay, so here's the new formula right here. And this example I have on the other sheet of paper, so we can do that together. Get down to here with your writing of your notes. It's V1 over T1 equals V2 over T2. Okay, and this is when the pressure is kept constant. Now the pressure volume thing was when what was kept constant? When temperature was kept constant. So Boyle's law is when temperature is kept constant. Charles' law is when pressure is kept constant. Okay, so let's give Charles' law a try then. The math is just a little bit different, but here's your formula. V1 over T1, making sure T1 or T is in Kelvin, equals V2 over T2. Okay, so if you look at this, it says 27 degrees Celsius amount of gas has a volume of 2 liters. So I'm going to say this right up here, then must be T1, and this is V1. What will it occupy? Okay, so that occupy must be what? Space, right? Because volume is space. So how much space will it occupy? So this is V2, which we're looking for, and this is T2. Okay, so before we plug this in, we have to change Celsius to Kelvin, right? So Kelvin then is Celsius degree plus 273. Okay, so Kelvin for this is 27 plus 273. Kelvin would be 300.
No.
And 300?
Yeah.
Okay, now notice there's no degree mark with Kelvin. It's just 300 Kelvin, or 300 K. Okay, so that would be our first one, right? Our second Kelvin temperature is 273 plus 87, 360. That's K2. Okay, so let's plug that in then. We've got 2 over 300 equals V2 over 360. Okay, so all you have to do for this to solve for V2 is what, guys and girls?
Times by 360.
That's all.
Multiply both sides by 360 because it cancels that out. Just like the factor label method. Okay. So, 720 divided by 300 equals V2 equals
0.4.
2.4 liters. Can you do that?
Yeah, I just did it.
Okay, I want to do, since we're kind of on a good, oh, do you have a question? Okay, since we're on kind of a roll here, I want to just do one more, the pressure equals force over area. So the whole piston thing, remember that? This is mostly for the kids that weren't here the other day. So we have this pistons in here, right? So this circle, so this is a hydraulic system. This is a fluid inside here, but it's more than a fluid, it's a liquid, because gas is fluid too. Liquids are not compressible, gases are. That's why this fluid has to be liquid. And Pascal's principle says that if I have a pressure right here, P1, throughout the whole entire enclosed liquid, I have the same pressure. So the pressure here is the same, pressure here is the same. The whole entire liquid has the same pressure. That's Pascal's principle. This is what we're using when we do hydraulics. So over here, this area, we'll say that area of that plunger is going to be 10. Okay. We'll say that this area here is 2. Okay. Let's say that I push down on this with a force, I push down with a force of 5 newtons. My question is, how much force do I get pushed out on here? Because if I push here, it's going to make that one go up, right?
A lot more.
Okay, so this, okay, but now let's see how this works. Because we could say P1 here equals force over area. But also P1 equals P2, which is force 2 over area 2. Keeping in mind that these things all go together, these things all go together, and since the pressure, like if I call this pressure 2 over here, it's actually the same as pressure 1 because of Pascal's principle. Does that make sense? So the formula boils down to this. Force 1 over area 1 equals force 2 over area 2. Any questions about that? Okay, so then we just plug and chug there. So for this one, we have force 1 is 5, area 1 is 10. Okay, so I'll go 5 newtons over 10, we'll say meters squared. And then force 2 is what we're looking for. Our second area, I better check. Oh, that's 2 meters squared. To solve for force 2, what do? You multiply both sides by 2, cancels out. So 100 then, divided by 10, equals force 2, which equals 10 newtons. Okay? Does that make sense? Okay, so that's kind of a sum up of all the different math problems that you'll have to do for the test. Now we just have to practice. No. Okay, I messed up. 2 times 5 isn't 10. It's actually, or I mean, isn't 100. It's actually 10. So the force, 2 then, would be 1 Newton.
That's about
Okay, and maybe that'll help you with your math problems.